Chapter 10, Section 6 has two big theorems in it, which really are the same thing. And it all centers around one big idea here. We're going to be measuring segments, the lengths of segments in circles now, instead of the angles. We've been working with the angles, and now we're switching to segment length. So that's a pretty big switch. So kind of get your mind around the fact that this is going to be about segments, not about the angles and lengths of the segments. But the big idea here is all segments that we're going to use in both theorems start at the point of intersection. Let me give you a demonstration of what's going on. Okay? Basically, this is a sketch pad here, and you'll notice that I'm measuring different segments. Okay? I'm measuring PA, PB, PC, and PD. I am at no point measuring the distance from B to A by itself. Okay? It's always PA or PB. Everything starts at the point of intersection. Now, you'll notice that the individual segment lengths, PA, PB, PC, and PD, are different. But the product of those is exactly the same. PA times PB equals PC times PD. And it doesn't matter where point P is. If it's inside the circle, the same relationship holds. If it's outside the circle, the same relationship holds. It doesn't matter where that point of intersection is. It doesn't matter if the point, if this is a essentially tangent line. Okay, A and B are the same point. That's what happens at a tangent line. Notice, well, it's off a teeny bit here because of rounding errors probably, but the same relationship holds. The product is still the same. Okay. Getting a little bit off there because of because I'm trying to move, okay, because I'm moving the points across each other. So if I go just a little beyond tangent, that's when we lose it. Okay, but PA times PB equals PC times PD. But what do you notice about every one of these segments we're measuring? We always go back to the point of intersection. All right? And it doesn't matter if the point of intersection is on the inside. PA times PB equals PC times PD every time. All right, that's basically everything we're doing in this section. Is that one idea, and we're going to practice that. This is what it looks like in actual theorem form. So we can look at the actual theorems here very quickly. Segments of chord's theorem and segments of secant's theorem. Not that important that you remember the names of these. We could talk about tangent segments and secant segments and external segments. They're going to use all those fancy words. Again, not that important that we remember those words. It's the concept that every one of these segments always goes back to the point of intersection. In this case, it's P. In this case, that was E. So, very simply, we set up and solve equations based on this. So I want to find first one here. First example is we're going to find ML and JK. Well, we set up our equation here. Our point of intersection is N. So it's going to be NJ times what other segment? It has to be along the same line, so NK has to equal NM times NL. And so we just substitute in our values. Nj is x plus 4, Nk is x, Nm is x plus 2, and Nl is x plus 1. Now there's a little bit of algebra to work on here. Nothing too horrible. But we are going to have to do a little algebra that we're not used to doing, and that especially over on this side where we have to FOIL. This one isn't bad. Okay, this is just distributive property. This gives me x squared plus 4x. This side I got to FOIL it out. So x times x is x squared. X times plus 1 is plus 1x. Inside is plus 2x. And last is plus 2. So x squared plus 4 equals x squared plus 4x plus 3x plus 2. Now, that looks horrible, but since it's just a single x squared on each side, I just subtract x squared from each side. and I get 4x equals 3x plus 2, and do the rest of simple algebra, I get x equals 2. Once I know the value of x equals 2, I can substitute back in very quickly to find ML. ML is going to be 2 plus 2, this is going to be a 4, this is a 3, this is a 6, and this is a 2. And sure enough, 4 times 3 equals 6 times 2. That works out. So ML is going to be 7, and JK is going to be 8. That was a really hard one. Now, for your first question of the day, we're going to do a really easy one. Now remember, my point of intersection is right here. And if I call these other points A, B, C, and D, and this is my point P in this case, you need to set up an equation using those to solve for x. And it should work out pretty nicely for you. Just telling you now, I should get a nice answer. So give that a try. What gets trickier is when the value of x is, or when the two lines intersect outside the circle, because it is so very tempting to set this up wrong. Okay? What most students are going to do, and this is wrong, is they're going to do 9 times 11 equals 10 times x. Because those are the variables they see, numbers they see in front of them. But that's not right. Okay? We don't ever use just the internal segment on its own. Okay? Those are big no-nos. We never use just that. We always start every segment at the point of intersection. So the numbers I'm really looking at here are the 9 times the whole thing. 9 plus 11 is 20. So 9 times 20 equals 10 times the whole thing. And here's where it gets a little tricky. The whole thing here isn't 10 times x, it's 10 plus x. So I get a little bit of distributive property to work with here. Because all the segments have to start at the point of intersection. What did I say on the first side? All the segments must have one endpoint at the point of intersection. All the segments had one point at the point of intersection. All the segments have one point at the point of intersection here. And now we just do the math. 9 times 20 is 180 equals 100 plus 10x. Subtract the 100. 80 equals 10x, so x equals 8. Once I know that, x equals 8, I could find out whatever I wanted, but in this case, all I want is the value of x, and we're done. Okay. Now, this really is, again, the same thing. If one of them is a secant and one of them is a tangent, we just take this tangent point and imagine that both endpoints, like I drew on the line before, like we did on the sketch pad that we saw, when I move my point on the outside, a tangent really is not a separate theorem here. This is actually a third theorem. Okay? But when these 2 points, when we create a tangent and the 2 points come right together, right there, we still have the same situation. Okay, I really should get PA-PBB. There we go. Okay, so it's the same theorem still. All right? We haven't changed anything. All my segments start at the point of intersection. It's just that both points of intersection have kind of merged into one here, so we count this one twice, EA squared. Actually, I don't want to do this as one of our, I don't want to do this one. This is kind of a tough one. So I'm going to get rid of this star. Delete. All right. And we'll do a different one in a minute. Let's do this one, though. Okay? So same thing. We take x times the whole thing, which is x plus 8, equals 16 times, where's the second part? Well, it's a tangent, so we're going to just multiply it by itself. 16, the second part's the same as the first part. Now, this one's tricky, and the reason I didn't want to do this is because look what's going to happen. X squared plus 8x equals 16 times 16, which is 256. Now, that's more difficult to solve. And now we're going to get into solving something that we haven't had to do since Algebra 1. I'm going to have to solve a quadratic because I don't have an x squared over on this side to cancel it out. So in order to do that, I have to bring everything to one side of the equation. And now I have to do my magic numbers in order to solve that. So I need two numbers that multiply, okay? And maybe you saw it this way, blank times blank equals negative 256, and blank plus blank equals 8. So I need two numbers that multiply to give me negative 256, and two numbers that add to give me positive 8. That's a little tricky, trying to find that. So I got to start finding numbers that multiply to give me 256. How do I do that? That's a kind of big number. Well, 1 times 256, that works, but that's not going to help me very much get to 8. 256 divided by 2 is 128, so that's 2 times 128, 28. That's still not going to get me to an 8 when I'm adding. So 256 divided by 3 doesn't give me a whole number. 256 divided by 4 is 64. Still not going to give me an 8. 256, 8, and 32 work. We're getting closer to an 8. 32 minus 8 isn't quite an 8, but we're getting closer. Okay, 16 and 16, that works. There's nothing that really works with a product there. Not liking this problem so much right now, which means we're going to have to revert. When I can't factor it, I have to revert to the quadratic formula. So that didn't factor. Even less nice. Because there are no two numbers that multiply to give me 256 and add to give me 8. So we go to the quadratic formula. Now remember, in this case, the A equals 1, the B equals 8, the C equals negative 256. And this is all review from algebra. You did this in Algebra 1. But it dives right in here. So what do? We plug those values into my formula. Negative 8 plus or minus the square root of negative 8 squared, minus 4 times 1 times negative 256 all over 2 times A, which is 1. Plugging these numbers in the calculator, it's negative 8 plus or minus the square root of 64 plus negative times a negative is going to give me a plus. 4 times 256 is 1024 over 2. Okay, so this is negative 8 plus or minus the square root of 1088 over 2. Or negative 8, when I simplify the square root of 1088, that gives me 2 root 272. 4 root 68. So 1088 divided by 64 is 17. Or negative 8 plus or minus 8 root 17 over 2. That's nice. Factor the 2 out of the numerator, that's negative 4 plus or minus 4 root 17. Boy, they gave us a really ugly example here. I'm glad I didn't give you this one to do on your own. So the numbers don't work out very nice at all. But here, negative 4 would be negative 4 plus 4 root 17 would be the solution. The minus wouldn't work. That would give me a big negative number, which doesn't make any sense for the value of x. I'm just going to double check my work here, because that does seem to be a strange number. X times x plus 8, which is x squared plus 8x equals 16,256. Minus the 256. It did not factor. I get negative 4 plus 4 root 17, which would be negative 4 plus 4 root 17, approximately 12.5. So checking my work, if I get 16 squared, should be about equal to 12.5 times 20.5. 256, yep, that works out. That is the correct answer. So that's a super difficult problem, just because we had to go to quadratic formula in order to find the value of x. Most of the time, you're not going to have to do that. Sometimes you might have to factor, but most of the time, you aren't going to have to do that. Most of the time, you can come up with something that's much, much nicer, which is more like this. All right, we get something like, make this 6 and this 10. And I'm going to make this 8 out here and make this x in here. This is going to work out much easier for you. So this is the one I'm going to want you to try. Give it a shot. Again, just another one where we're trying to find the radius of the aquarium tank. So if I set this one up, again, it's point of intersection of point in the circle. 20, since it's a tangent, we multiply it by itself, equals point of intersection of point in the circle, 8 times, and then 8, this whole thing is 2r, so 8 plus 2r. So you get 400 equals 64 plus 16r. Subtract the 64. That's 336 equals 16r. So 336 divided by 16 is 21. So the radius of that aquarium tank is 21 feet. As you set that one up. So much easier situation than when we have the big quadratic. Clearly, when the x is on the outside, it's going to be more complicated. When the x is on the inside, we aren't going to come up with a quadratic or anything that requires factoring. We'll spend more time talking about the factoring and stuff like that, and we will run into a few problems with that. So, all right, that's what we got for today.